Okay, let's take a look at an interesting application of differential equations. It's a mixing problem. Let's read it together. This is from section 5, and it's the very end of what we study in chapter 1. So, a tank initially contains 40 gallons of pure water. All right, so as we go through this, maybe some of this stuff's important. All right, brine containing 1 pound of salt per gallon enters the tank at 2 gallons per minute. So that's kind of confusing. 1 pound of salt per gallon enters the tank at 2 gallons per minute. And the perfectly mixed solution leaves the tank at 3 gallons per minute, okay? Thus, the tank is empty after exactly an hour. Does that make sense? Okay, so you have a tank full of water, 60 gallons. In comes 2 gallons per minute, but out goes 3. The net effect is you lose a gallon every minute. And there's only 60. So yeah, it does make sense. So it has 2 questions. Find the amount of salt in the tank after t minutes. And the second question, what's the maximum amount of salt ever in the tank? I'm going to stick to part A, and I can kind of point you in the direction of part B if you're curious about it. This is straight out of the book. And so let's take a look at this thing. All right, so what we're interested in is part A. Find the amount of salt in the tank after t minutes. Okay, that sounds like, is it 5 gallon or 5 pounds? How many pounds? It really is. All we have is it's pure water, and then salt water comes in, and mixed salt water goes out at a faster rate, and we got to come up with it. They didn't say anything. The only thing I know is that we start with 0 gallons, right? So I could say something like this. If we do a little table, we could say when t is 0, s is 0. So you could also say s of 0 is 0. That's an initial condition. Let's look at this as a differential equation. We're going to look at it as the rate of salt, okay, changing with time. How does it change? Well, in comes 2 gallons per minute. Each gallon has a pound of salt. So I'm going to start writing a differential equation. The rate at which the salt changes with respect to time, okay, oh my gosh, yeah, welcome to differential equations, is equal to 2. Because why? Well, because it's 2 pounds of salt per gallon, and it's coming in at, oops, I did it wrong. I went too far. How many pounds? 1 pound of salt per gallon, but it's 2 gallons per minute coming in. So that means here comes a gallon per minute. Each gallon has a pound of salt. So, 1 times 2, if you will, is 2 pounds of salt per minute coming in. So it's increasing at a constant rate of 2 pounds of salt per minute. That's why I'm saying ds dt is just 2. But here's the thing. In this tank, and you've got 60 gallons, and you've got this thing coming in, it's called salt, and in comes the salt, and it's 2 pounds per minute. And it goes in here and it sprinkles all around, all the salt's in here. But then what happens is out pops at 3 gallons per minute. We're losing the solution. But that 3 gallons per minute is not written in terms of salt. What we had over here was let me write it out. 1 pound over here, 1 pound per gallon times 2 gallons per minute. I want to have so many pounds per gallon times 3 gallons per minute over here. And that will, folks, that's going to be the rate going out. You're losing that salt because it's draining away. So that's going to actually have a negative effect on the amount of salt. But the thing is, the question is this one, how many pounds per gallon? And the answer is, that's what our variable is for. The variable S, let's write it out, S equals pounds salt in the tank at any minute or time t, let's say, at any minute, okay, or fraction thereof. So S is the pounds, and the number of gallons that's in the tank, I would want to say 60, but it's not 60 because it's 60, and then it's 59. And then remember, it's going down. So do you have an equation, a simple linear equation? Yeah, I do too. The amount of gallons is, it starts out 60, but then every moment in time, it drops down by whatever T is, 1 gallon per minute. And so that's what we get. We get, for our differential equation, we have S over 60 take away T times 3 gallons per minute. That's your differential equation. Okay? Take a look at that thing or pause. Now, what it is the rate, I should have written this first, of change in pounds salt in the tank is equal to the rate pounds salt in minus the rate pounds salt out. And we had to get fancy with, well, you know, how many pounds per gallon, how many gallons per minute. That's what makes these setups so interesting. The rest of this is routine solutions, okay? So let's do it. I'll write this, and I know that actually there's a clever way of solving this as a separable differential equation, which you can do, and you can explore that, but I'm gonna do it as non-separable. I'm gonna simply write, hey, I've got S prime, and I'm gonna bring them over as minus 3 over 60 take away T, S is equal to 2. And now someone says, solve this as a differential equation. So the struggle at the front of these problems is to get this differential equation right. Okay, and I think you have a couple, 2 or 3 problems to do in your assignment. Okay, so let's solve this thing. Yeah, I'm gonna do the integrating factor. And what we do is we take this, whatever it is, including the sign, so it's got a negative 3 over 60 minus T. We're going to integrate that. And for that, we'll have to go let U equals 60. You got to be really careful, because what we get is what we end up with is du is negative dt. So we have a negative floating around. All these steps are important, or else we get messed up. So we already have a negative, right? Okay. So when we integrate this thing, did I do that? No, actually I made a mistake. Look at this. I brought it over as a minus. Do you catch that about 5 minutes ago? It actually should be plus. Should be plus. That's a boo-boo. Okay. So now we don't have this guy. Let's erase the minus sign. That right there is an example of be careful, be careful, be careful. So we end up in this case, if you integrate, you get 3 over u, which is really, you're going to have, and the negative, so you have a negative 3 natural log of 60 take away t. Okay. And then, of course, since we're doing this as a integrating factor, we take e of that. And remember how this number can come in as a power if you're dealing with natural log, so that you can cancel the e's. So our integrating factor is really, I'll write it this way, 60 take away t to the negative 3 power. Okay? So for this equation here, we multiply everybody by it, and you know I'm funny about this, so I'll just do it myself this way. I'll go 60 take away t to the negative 3 times s prime plus 60 take away t. Okay, I'll try to go faster, but some people go, don't go so fast. You can pause it. 60 take away t to the negative 3, but then it multiplies with 3 over 60 take away t times s. And on the other side, 2 60 take away t to the negative 3. So we multiply through with it when we're dealing with these separable differential equations. I want you to take note of this again. What we have is 60 take away t to the negative 3 s prime. And look at this one. We're going to end up with plus 3 60 take away t to the negative 4 times s, and over here is this thing. Now the thing on the left, okay, observe, okay, this guy's derivative is this guy right here. Okay, this is like looking at f and of course s prime, or you can call it g prime. And over here, this is f prime g. And it's really nice how the integrating factor works for us that way. Okay, stop gloating, Weber. Okay, I'll keep going. So really what's on the left-hand side is the derivative with respect to time, product rule, of your integrating factor. It always goes this way if you've done it right, times your function you're looking for, which is s. And over here is this thing. Okay, so I'm going to need your help here. We still have quite a bit to do. We're going to integrate both sides. So we bash away that derivative, and we're left on this side with 60, take away t to the negative 3 times s. And on this side, we have to integrate it. It's a u substitution, right? So we have, I think it's going to be a negative, I'm going to bring the 2 out, right? Am I doing that right? So negative 2. That's going to be like, I'm thinking about like u is 60 minus t again, du is negative dt. So we have a negative, that's why I put a negative in front of the 2, okay? And then what happens is you're looking at an integral of u to the negative 3, which becomes u to the negative 2 over negative 2. So we're getting over negative 2, and by the way, those cancel, that's sweet. And then it's u, which is 60 take away t, but this time to the negative 2, and watch out, here comes your plus c. We've done it. We've gotten this far. I think at this stage what I'm going to do, what we have to do is solve for s, and we have to figure out c to get the particular solution. So I'm going to come in and I'm going to multiply by 60 take away t to the positive 3. It'll cancel, leave the s, and it'll leave over here, the 2's are gone. So basically you're left with 60 take away t, and then you have plus c times 60 take away t to the 3 when you multiply all the way over. So we have our function, we just don't know what c is. But now go all the way back. Remember when time t is equal to 0, this table I was doing, you get 0 for s, because it starts off with no salt. So we're finally going to plug that in. I'm going to put a 0 here, a 0 here, a 0 here, and hopefully we can find c. So it's equal to 60 take away 0, 0 is equal to that, plus c times 60 take away 0 cubed, okay? So we have 0 is equal to 60, and we have plus c 2 times 60 cubed. So that's telling us that c itself is negative 60 over 60 cubed, which is going to be blah, blah, blah. I think it's going to be negative 1 over 3600. Folks, this is it. We did it. S of t, the function itself, is 60 minus t, and then minus 60 take away t cubed all over 3600. Okay, that's a interesting looking curve, isn't it? As t approaches 60, we run out of water, don't we? Okay, as t approaches 60, the salt, look at it, 0 and 0, you have no salt left in the tank, okay, because the tank is empty. And so that is how this guy gets solved. The next part, if you go for part B on your own, and you want to know where the max salt is, what I would do is I would take this function. There's different ways. Maybe there's a more clever way to do it, but in Calc 1, what they did is go, okay, take S prime, set it equal to 0, find your critical numbers, and then figure out how much salt there is. I went ahead and did it. You can check my work, but what I got was T is equal to like 60 take away 20 radical 3 or something. I think that's about 25 minutes. So about 25 minutes in, you have the most salt, I believe, unless I made a mistake in the math. But go ahead if you want to check it out. And boy, you know, the setup of that is the main thing. And then all the steps there, you got to be real careful with it. But if you understand it, okay, you'll score well. I'll watch your work and go, oh, too bad, like watching you guys on a trapeze or something. Okay, that's it for this one.